Good afternoon, everyone. Welcome to the last stretch of the course, Introduction to Data Science and Computational Thinking. I just want to paste something in the chat room now, so everybody look at your chat room and get copy and paste this link somewhere. This link has all the resources that we've given in the course. It's including the link to the videos. So please make sure that you copy and paste that link and keep it safe somewhere, right? That's the first thing. Secondly, I will send out an email about a questionnaire later today. You'll have until about Monday or Tuesday to complete it. There is attendance requirement. But I'll let you know that once I've had conversations with the National Institute of Theoretical and Computational Sciences, who are the people who are going to be giving you the certificate if you qualify for it. Now, for those of you who may not qualify for the certificate, I don't think you should worry about that too much. The main purpose of the course is to get the skills in Python and in data science, right? And as long as you are continuously learning and gaining those skills, I think you are better off than you were a week ago. Well, at least I hope so. Lastly, there is exercise I put up on the same link. That is a final exercise that Jan set up. It would be good if all of you try that. You don't have to submit it, but we will put up solutions later during the weekend. Right, so there is a final.ipynb file as well as Excel CSV file called asteroids. You should use them together to answer the questions in the ipynb file, and we'll put up the solutions. Right, the requirements for the certificates are filling in a questionnaire that I'm going to send to you either later today or tomorrow, and then there's an attendance attendance part to it, which I need to figure out and calculate. So it's also not fair to tell you now if I knew what it was, because some of you, it will be unfair for all the people who've been attending previously. Either make it clear up front or at the end. But the main thing is that you're here and you're learning, right? Okay, without further ado, let me hand it over to Jan Klopper. Jan.
There you go. Can you hear me?
I can hear you.
Great stuff. Let's share the screen. Desktop number 1.
And while you're sharing the screen, I just want to say, it won't be 40 pages, Albert.
It won't be what?
The questionnaire won't be 40 pages.
Oh, no.
It has to be Albert who said that.
Okay. Afternoon to everyone. It's a Friday afternoon. Congratulations that you can make it on a Friday afternoon. That's always probably the most difficult time, at a conference. Usually those are the talks that no one attends because people have other priorities on a Friday afternoon. So I'm really glad to see all of you here. And thank you. It's been a wonderful week. I said there in the chat room, thank you for everyone's tweets. I love seeing all those tweets come through. And let's keep on the conversation afterwards. Certainly the School for Data Science Computational Thinking is quite open, and we want everyone to get on board. And I hope during this week, one of the messages that hit home for you is that this is a big community. There's a big international community, and you can definitely play your part in that community. Look out for the conferences as they came along. And then for today, what's on the menu for today, of course, you didn't have to do any exercise because I'm going to introduce you to something brand new today. And before we get there, though, you had a good session yesterday. What I wanted to show you is, if you work in data science, kind of what does your computer look like? What kind of resources do you use? So give me a couple of minutes, and I'm just going to show you around. So here my screen. So if someone can let me know, Kanshi, that everyone can see the whole screen.
I can see the Kaggle page at the back and the Predict Malicious website XGBoost.
And can you see my icons on the left-hand side?
Yes, I can.
Okay, so I just want to run you through those and just show you some of the software that is used in data science. So apart from the browsers that I always keep up here on top, and Microsoft Outlook and those kind of things, this is kind of the software that we're going to talk about. I'll leave this little terminal for last, perhaps. So one of the first ones you'll see there is my Wolfram desktop. So that's the Wolfram language, Mathematica as it used to be known. A lot of the math heavy stuff that I do, I still prefer the Wolfram language over Python because it's really a nice computer algebra system for symbolic computation. So if you're not necessarily working with numbers, but you're working in symbols, it's still one of the best languages out there. Then you see RStudio there. So R, I would put right up there with Python as far as data science is concerned. If you've got any background in R, all of the stuff that we've done this week and we're going to do today, you can do in R. And RStudio is the coding environment for R. Again, both R and RStudio, you just download free of charge from the internet, and you can do your work in Python on R. And those questions that are usually online, should I study Python or should I study R? Well, you should do both. There's no reason, once you do one, learning the second one, as I mentioned in the beginning of the week, is just so much easier. And then the real coding environment that I would use most of the time, I spoke about that before, that's Visual Studio Code. So I'm just going to open that for you. Let's give you sort of an idea what Visual Studio Code looks like. As I mentioned, I work in a dark theme most of the time, but you can just set the theme for, let's go down there, preferences, themes, color theme. Let's do default light, and there you go. Inside of VS Code, Visual Studio Code by Microsoft, you can create notebooks. So this is a Jupyter notebook right inside of VS Code, but then also you can just have normal files. So this is what the code would look like. So there's not this ability to do this verbosity, writing paragraphs of text and making titles and subtitles. It's just about the code. So you can do that, of course, or you can create a Jupyter notebook. So now I have the ability to do all of this. This is a nice, a nice little graphic there. And then you can do anything that you can do in a notebook, you can do here as well, including creating these nice sort of goofy looking plots if you wanted to as well. So that's VS Code allowing you to create notebooks or just write straight up code that you don't worry about any of the verbosity or extra features that you get in the notebook environment. So check out VS Code. You get the ability to download plugins, and you'll see there's my Jupyter plugin, and then also Julia, C, C++, and my Python plugins. I can use all those languages right here inside of VS Code. So if you're getting into data science and you're doing some work where it really just is about the results, not creating a research document as you would with a notebook, but if you want to create a notebook, you can do that right here as well. So that's certainly a very useful tool, and probably where I spend the majority of my time. It has a lot of extra features, code completions, IntelliSense, and all sorts of other things. If you want to step things up a little bit more, there's also this JetBrains toolbox. And from the toolbox, you'll see I have PyCharm. So PyCharm is a coding environment specifically for Python, but you can also write R code in there. And that's a whole professional development environment. So if you want to use Python to write games or create websites or full featured applications, you can certainly use PyCharm Professional. And this JetBrains, they have all sorts of other tools as well. So if you want to write JavaScript or other languages, you can certainly do that as well. And right here at the bottom, you'll see PyCharm Edu. So there's an educational version as well. I've got the professional version here. So the educational version, you have to be a student or staff at a university. So I'm not employed by Stellenbosch University, so I have to pay for this professional version. There's also a free community version that has a lot of the functionality, but I think the professional and the educational one that you see here at the bottom, those are fully featured. So that's another coding environment. And then I want to show you just a little bit about using this on your own system. So how do you get hold of all of this? And the place that I would have mentioned before that you can just do Google search for is Anaconda. So you can just do Anaconda and Python, just Google those. It's going to take you to this download page. It would be one of the first ones that pop up on a Google search. and it'll detect your operating system, whether that be Windows, whether that be Mac or Linux, and you can download and install it. That'll give you a graphical user interface, a program that has got nice little buttons on it, and you click the Jupyter Notebook button and a Jupyter Notebook opens up. So that, and it'll install Python for you. It'll do the whole thing. And a nice graphical interface, downloads all these packages that we've been using, NumPy, SciPy, Plotly, all of these get downloaded for you. And there are also hundreds of packages that you can simply just add to your installation. So it's a nice little program. So that's Anaconda that you can search for. And Miniconda is a sort of a smaller version of that. And it just takes away the graphical user interface. By that, I mean a program, like the program that you open up on your computer. So it has all of Anaconda except for the graphical user interface. So you have to type everything as a command. And that's what I prefer to do. So I'll just show you a little bit about a professional or data science, sort of what it looks like. If you open on a Windows your terminal or your command prompt, I should say, or once you've installed Miniconda, let's just go back there. So just go down and install either for Windows, Mac OS, or Linux, and install that. And if you open your command prompt then or your terminal window, you can just type something like conda env list, and that'll give me all my environments. And what you tend to do as a data scientist, you keep all your projects separate. So you'll have this base installation of Python, and we don't work in that base installation. We create little virtual environments or little projects, and all your work goes inside that project so that you can install different versions of packages in your different projects. And they won't clash with each other. So you can see here, I've got some packages here. One I call data projects, working also on graph theory. I have a specific package just for mathematics, some social network analysis, PyTorch, and TensorFlow. So those will be all my packages. And then all I have to say is conda activate. And let's do data projects. Data projects. And now I'm here on the left-hand side. You can see I'm in my data projects environment of Python. And inside of that, I can just install all the packages that I want. And as I say, if you do the Anaconda install, you won't have to do any of this typing. Then it just becomes clicks in a program. But some of us enjoy more having this control over having to type the code. So there is one of the packages that I want to introduce you to. Is just the Spider package. That's scientific Pythons for, that's where the term started, Spider. So it just takes a little bit. It's a big program to start up with. So I just want to show you that coding environment. And many people in the data science world still prefer, in the scientific world, still prefer Spider as their coding environment. So this is what Spider would look like. And so you install Anaconda or Miniconda, and then you install this as a package. And this is what it starts up like. And you can see it looks very much like VS Code. And it's a nice environment. On the right, your variables show up, your plots show up here on the right-hand side, you write your code here on the left-hand side, and you've also got a live interactive Python session on the bottom right. So it's also a very nice, very often used coding environment, and many of the tutorials that you'll find online, make use of Spider. Then, of course, if you have installed it, you just type Jupyter Notebook. Once again, if you installed Anaconda, you don't have to type any of this. There'll just be a button that you push, and then Jupyter Notebook starts up. So I just type Jupyter Notebook, and then you're going to see it looks very much like the environment that we do in Colab, because Colab is built on top of Jupyter. And there is my Python 3 kernel. So I just start a new Jupyter Notebook, and lo and behold, you can do all of this on your own at home. So you don't have to use Google Colab. So Google Colab is, of course, great for collaboration or for teaching. But if you are going to do some proper data science, these are the tools that are commonly used. And then if you are into teaching others and spreading the news and information about, I suppose, about data science, you'll see my DaVinci Resolve, Final Cut Pro, Motion, and Luminar AI, so that I can create videos, video lectures and materials, and do my video editing. So that's sort of what a data science, I suppose, desktop looks like. So please take note of some of these programs. have a look around and see which one is going to work for you. As I said, I think most people have gravitated towards using Microsoft Visual Studio Code, and you can install it on a Windows machine, on a Mac, and on a Linux machine. It's available on all the important operating systems, so that's not an issue. But if you want this environment that you're used to now with Google Colab, certainly give Anaconda. So just search Python Anaconda, take you here. That's the graphical user interface, or just search for Miniconda. And if you want to work in a terminal environment, such as I've done here, you can certainly do that. So back to today. So let me just shut down. I'm just going to shut down this terminal that I've opened up. So I've created a session, and I need to just get out of the session. So let's quit the session, and the session is quit. So once again, I'm repeating myself, but you won't have to do any of this if you install Anaconda. So I just deactivate my environment, or you won't see that at the bottom of the screen, but I deactivate, and I can just simply close that up. Someone asked yesterday, or we spoke very briefly about what kind of books you can read about data science. Of course, all I've done here is, instead of compiling that list, I'm just going to show you rather how to do it yourself. So I've just typed the online book Python data science. You can put the term free in there if you want to. And then this sort of thing comes up, 100 free books on data science. And you can, or 10 books on data science, not all of them would be free. Here's 9 free books on that. And one of the best ones that I mentioned yesterday that I quickly came up on the screen is this book by Jake van der Plas. I know there's a new one. I'm not quite sure if the new version is out, as I mentioned yesterday. And you can buy it on Amazon, of course, but you can read it online. So it starts there, as we did with data manipulation with pandas, an introduction to pandas objects. So it's both a book. Of course, you can see here it was written using a notebook. So it is very much the way that I've used to teach you in this. It'll be very familiar to you, and it's an excellent book with a bunch of resources, and can touch obviously on much more than we did in the short week that we had together. Now comes the exciting bit. So that was just a brief overview of kind of the tools that are used, and some of the coding environments. And we really have this embarrassment of choices here. And sometimes you just get tired of one environment and you start coding in the other, in another environment, and they all work very, very well. This ecosystem has really matured, and again, part and parcel of the success of Python, and for the same reason, R in the world of data science. So today I want to introduce you to machine learning. Most of you, I think, would have read at least the notes or played with those notebooks on machine learning, and introduction to machine learning, and will know that machine learning is a form of artificial intelligence. So artificial intelligence is the overarching term, but that's also a subset of a greater idea, and that's AGI, and this idea of general artificial intelligence. And the idea there is the AI that we deal with machines, and machine learning being a subset of that, is that we're not anywhere near this idea of generalized intelligence or artificial general intelligence. That's way into the future, where we'll have sort of the science fiction version of artificial intelligence that we see in movies and TV today. So artificial intelligence, a subset of that would be machine learning, and a subset of that would be all these algorithms that we use, whether that be deep learning through deep neural networks, or random forest, all kinds of ensemble techniques, and then much more straightforward techniques such as the k-nearest neighbors that I made a video for you on. There we go again. I want to introduce you to probably one of the biggest communities when it comes to machine learning. And as I say, you get into data science, you can do your linear modeling, etc. Well, some people, of course, just get or their work allows them to concentrate on machine learning. And one of the greatest communities and web resources for that is Kaggle. So it's just, as you can see there, kaggle.com. Let's increase this screen resolution one more time. So that's kaggle.com, as you can see there. And what this is, if we scroll down, first of all, it's this online community of all sorts of resources. I think what Kaggle is most noted for is, let's just try, I'm just going to redo this page, is competitions. So if we click on Kaggle competitions there, we see the competitions that are ongoing at the moment, and you see the prize money for these competitions. So these are usually companies, if you don't know Kaggle. If you do, of course, you know what I'm talking about. So private companies and other institutions put out huge competitions, usually for their own gain, but they'll put enormous prize money on this. You see there $100,000 of prize money for that competition. So individuals, or more commonly groups, get together of data scientists and they'll tackle some of these problems. And there's leaderboards. So you can see here the one on COVID-19 detection, RSNA detection. There's 1,175 teams have signed up for this code competition, and everyone is vying on this leaderboard, you know, who can create the best machine learning model to make the most accurate predictions here, and they'll partake in that big prize money. There's also the idea that, you know, you personally start, if you do a lot of these competitions, you can personally start ranking, and you can climb up the ranking board and become a master of machine learning. So, you know, I suppose that's what what Kaggle is famous for, is companies putting out huge competitions there. But Kaggle is also famous for open data sets. So if we were to click on data sets, you can start searching for data sets. They've got some categories there that you can search in, and it's absolutely wonderful. So let's do something like earth science, let's do that. And that's going to bring us, you know, you can filter by the kind of data set that you want, how big it should be. Should it be CSV files, or should it be images, or should it be text? And you can really hone in on all these open data sets. Let's try and find a specific one. Let's do, what's one that I've seen lately? Eurosat, I think it was, yeah, Eurosat dataset. So there's the Eurosat dataset, for instance, 2 GB. This is the kind of page that's going to pop up. And what you can see on the right-hand side is new notebook. So of course, you've got to sign up. It's a free account. And up here, you can see just how to register or sign up. But if you've gotten to one of these pages, you'll see there's some discussion board. There's some information about what is in this data set, and gives you information of all of the files in that data set. And all you have to do is click on New Notebook. And just as we had with Google Colab, this opens a Jupyter Notebook for you. So this should look very familiar. And with the added bonus that the data set is right here on the right-hand side. Of course, I can close that. We can open it. And the images, so this will be satellite images, and all the data is here on the right-hand side. So that makes it very easy for you to get going in machine learning, because you've got your free of charge Jupyter Notebook here. And once you've found the data that you want to work in, you can, you know, the data is right there. And of course, there's a little button for you. You can add your own data to this open session as well. So that's where I want to take you. That is where I want to take you today. And I don't want to reiterate everything that I said during the video lecture or in the notes. What I instead decided to do is, let's take one of these data sets, and the one that we're going to do is a particular real world problem, and that's to try and predict the diameter of asteroids. So there's lots of information available through the National Aeronautical and Space Administration. So if I can use I don't know, ever, you know, pronounce it like an American or like a Brit, so it's NASA or NASA, put out this data, and there's a lot of that data, and you can also search for open data from NASA. So if you're into astronomy, of course, you'll know all these things that I'm talking about. NASA, they use a particular model to predict the diameter of asteroids. Of course, the big ones are easier, but it's not like we have satellites orbiting in the asteroid field with a little tape measure to measure all these things. So we have to use other techniques. So we're going to play with this data set that's right here, the prediction of asteroids. You'll see there's 2 CSV files there. We're going to use the asteroid.csv. And we're going to work with that. And I've already typed all the code today, and then of course we'll download this and share. But you can see if you become part of this community, there's also this nice share button up there. So it's easy for us to to share these notebooks with each other. So I'm going to use NumPy and Pandas as always. And then we're going to use the scikit-learn library today. So bring up the scikit-learn website here, scikit-learn website. Most of you, or some of you at least, I'm sure have been curious and have a look at scikit-learn. And you can see it is a massive machine learning library in Python, really massive. And their website is very nice. It breaks it down into the kinds of problems you want to deal with, a classification problem. So if you've seen the notes or looked at the video, you know classification problem is where our target variable or our outcome variable is categorical in nature. Regression problem, which is what we're going to deal with because the diameter of an asteroid is a continuous numerical variable. So that will be a regression problem. And then also for unsupervised learning, that's where we're not interested really in that's the opposite of supervised learning. In other words, we don't have this target variable or outcome variable. We want the machine to learn patterns in our data. And one of the best ways for that is to use clustering. And so, of course, they have all sorts of information for you there. I'm going to touch on data pre-processing. We've mentioned a little bit of that. So there's certainly a whole section on that. And then other more advanced techniques such as dimensionality reduction using, say, for instance, principal component analysis. Everything is available in scikit-learn. It really is fantastic. Of course, if you're going to do my course on using machine learning, I should say, deep neural networks, deep learning, one of the two leading packages there is TensorFlow. TensorFlow is brought out by Google, so it's the Google initiative, creating this open software library for Python, but also for JavaScript. So you can also, if you code in JavaScript, you can also make use of TensorFlow. So there's the website for TensorFlow and deep neural networks and all sorts of interesting information and tutorials, etc. It's again just this embarrassment of riches that we have if we want to learn about these things online. So scikit-learn. So what we're going to import from there is from the model_selection module, we're going to import the train test split function, and we'll talk about that in case you haven't gone through the notes. So let's run that line of code. And then from the set of ensemble methods, so this ensemble module in scikit-learn, we're going to import the random forest regressor. And because we did linear regression yesterday, they also have linear regression. They don't skimp out on that section. So from the linear model, linear_model module, we're going to import linear regression as well. Did we import random forest? There we go. And then we're going to, because this is a regression problem, what we're going to use as our metric is the coefficient of determination. So from scikit-learn.metrics, we're going to import R2 underscore score function. So we can work out some R2 values, R squared values, I should say. And then from pre-processing, we're going to import this standard scalar, and I'm going to say something about that. And then as per usual, we're just going to import our Plotly, our normal graphing libraries there, but I'm also going to make use of Seaborn. So I'm just importing matplotlib and Seaborn as well. So let's just go through the data. If you're not an astronomer, there are all the variables that are in this data set, this asteroid.csv. So the first one is the name of the asteroid, and the second one is the semi-major axis in units of AU, eccentricity, the inclination with respect to the XY ecliptic plane, the longitude of the ascending node, the argument of perihelion distance in astronomical units, etc. So you can see all the variables there. And the one that we're interested in, that's going to be our outcome variable, is this diameter, the diameter of the asteroid in kilometers. Now, I mentioned before NASA, they have a model themselves, and they use only 2 of these variables in their prediction. So the idea when this data set came out, of course, is can we do better than them using all this information that we do have? So when I share this notebook with you afterwards, you can certainly look through that list of these. Now, because this data set lives right inside of Kaggle, when I do my read_CSV import, all I have to do is, you can see the name up there. It's prediction-of-asteroid, and then off the screen it goes dash diameter. So I'm just going to say /Kaggle/input, because you can see there it's in the input folder. Let me just try and increase the screen resolution just a little bit again for you. You can see, there we go. Prediction of asteroid diameter. It's right up there. /asteroid.csv. So you are importing directly from Kaggle here. We don't have to log in. And of course, you log into your Kaggle account, but you don't have to re-log in as you do with Google Colab. And I'm setting this flag or this argument low memory equals false. This is to do with the size, of course. You might run into problems importing larger data sets here on Kaggle, so that's always a nice flag to use. So let's have a look at the first 5 rows using the head method. And you can see there, showing the first 5 rows of 27 columns. And you can see the 27 columns there. Now we're going to run into problems. Of course, we don't see all of them here on the screen, but look at this, NaN, N-A-N, not a number. So certainly there's some missing data in this data set, and we're going to have to deal with it. And that's why I wanted to show you this particular sort of real world example so you can see how to tackle these problems. So let's call df info. And that, of course, gives us information about our data set. On the columns here, on the left-hand side, you'll see all the columns or the variable names. And you can see for some of these, there's a great lot of missing data. So for instance, in G, what was G again? I'd forgotten for a moment. Oh, I can't find it there. Maybe I hadn't typed all of them in there. But anyway, there's only 119 non-null values. So there's certainly a lot of missing values. And you can see some of these go up to 839,000 rows of data. If we look at the diameter is only known for 137. So there's certainly, even in our target variable, there's a lot of missing data. And so what we're going to do here, because this is a problem, we want to see this as a classification problem. We want to build a model where we have this target variable that is known. This is a supervised machine learning model. So we absolutely want to know the value of our outcome variable, which is the diameter, or thing that we're trying to predict by creating these models. So what I'm going to do here is just drop all the rows for which the diameter was not captured. So that's going to lose us a lot of data. And it does get us into this idea of how to deal with missingness. And there are various classification systems for missingness. The the 3 ways really in which to see it is missing at random, missing not at random, and missing completely at random. Those dealing with missing data, and imputing, that means calculating values that you can put into those empty cells. Data imputation, we've mentioned before, that is a really big field of study. And I won't go into the details there. To keep things easier here, I'm just going to delete all the rows for which we don't know the diameter, so that this is a real classification problem, so that we know exactly what the outcome is going to be. So I'm just using df.drop_na, and the subset, you just list all the rows all the columns that it should look at for this missing data. And I'm saying just look at the diameter one and throw away all the rows for which we don't have information that's in the diameter. So if we look df info now, we see, well, we've come down quite a bit, so that everything is now in the range of our diameter, which is 137,000. So not too bad. We still have data on 137,000 asteroids here, 137,681. But there's still some others that we might want to get rid of. So all I've done now is, if you only have data on 119 of those, it's sort of one of the ones that I want to get rid of. So I'm just going to be very heavy-handed here and just get rid of all the columns for which we have very little data. Of course, if you're going to do this properly, you'll have to go through them one by one. You'll have to decide if you are just going to discard those variables as predictor variables, or are you going to do some data imputation where you can use various techniques to fill in the blanks. And from the easiest thing to do is just to fill in the mean or the median of that, to very complicated ways of imputing your missing data. And you can actually use machine learning to use the other columns to learn, what values should you can impute those missing with. So the easiest thing to do, of course, is to be very heavy-handed and to save time. And because this is just an introduction, I'm going to be very heavy-handed, and there's quite a few of these columns that I'm going to get rid of. And I might be discarding very useful information here. So of course, it takes a lot more diligence than what I'm dealing with now. And if I call df info now, you can see I've got a lot less now, but all my columns that I now do have, they have 137,681 data points. So I'm not missing anything anymore. And what I want to warn you against is this info doesn't always tell the whole truth. So there might still be some columns that you might have to go and really search for weird entries that are really missing entries. And even though it says now non-null, that's not the end of the line. And this is part and parcel of this idea of data wrangling, working through the data, getting it right before you do your machine learning. It's a very important step. So one thing that I noticed, our diameter, which is supposed to be a continuous numerical variable, is still denoted by pandas as being an object, which makes it a categorical variable. And we said this is the regression problem. We're trying to predict the diameter of an asteroid here. And so that better be numbers. So just to confirm that, I'm going to call that pandas series, so df.diameter, so that only gives me back that column, remember? And then I'm calling the dtype attribute on that, and I see it's dtype O for object, and that's just wrong. So let's just have a look at the first 5 rows of that pandas series, and I see indeed it was numbers that were put in, but we know it's JuliaCon at the moment, the big yearly conference of Julia, and I was watching some of the talks at the conference last night. And it was all about the pain inflicted by us, by the developers of spreadsheet software, unnecessary pain and suffering. And so even if you export your files as CSV, where it strips away some of the stuff that gets added by Microsoft or by Google and Google Sheets and Microsoft Excel, there's still a lot of pain involved with tabular data files. So we can fix that, because even though someone marked this probably as text, we can fix that right inside of pandas. We don't have to open spreadsheet software to try and fix that. So I'm going to overwrite this df.diameter, that column, so the series. And I'm using the pandas function to_numeric. So to numeric, and what I want to change to numeric is that column. And if there are any errors that it runs across, because there's so many different scenarios that happen inside of CSV files, I'm just going to say, use this setting for the errors keyword argument, and that is coerce. So that just says you can look at the to_numeric function, and you can see the various flags you can call on this errors argument. And coerce is sort of one of the stronger ones. It's sort of bullying everything into being a number. And it's done that. And so it's changed my diameter now into my diameter column into numeric. But it's a sneaky thing. Always check up after the fact. So what I'm going to do here again is just call df diameter, and I'm using this time the method is NA. Remember, that's going to return true or false. Go row by row down that pandas series df.diameter, down that column, and it's going to see is it an NA, or not a number, or a non-existent or empty cell. And it returns true or false. And remember, true is 1 and false is 0. So if I sum over all of those, if there was no empty cells, I should get a sum of 0, because this is all going to be false, 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 false. And lo and behold, if I did that, when I sat and designed this this notebook, first of all, I had trouble because I thought that I'd caught everything by my errors equals coerce. And by the fact that if I looked at this info, everything seemed to be there, but lo and behold, there was still one empty cell after all of that. And it wasn't really empty. I think the real problem was it was really badly encoded in the CSV file. But you can well imagine we have a spreadsheet here basically of 137,681 rows. To go, if you open a spreadsheet file and go look down that file for the empty, if you just want to quickly see if there's anything empty. Of course, in the spreadsheet software, there's, you can do stuff in Excel to do, find those empty values, empty cells too. But there certainly was still one. So what I'm going to do now is, again, now that it's coerced to numbers, I'm going to do this exact same thing. Drop in a subset equals the diameter column. So just to get rid of that last one, and indeed now we've lost one, it's now 137,680. So we certainly lost that one. So I've sort of cleaned up the data now. Now I didn't even look at any of these other other variables, and that, as I said, you have to go through them one by one, not only to decide what to do with them, decide if you want to do data imputation. There's lots of other things that we still have to do. But what I've mentioned to you now, it gives you sort of a flavor of what you have to go through before the data that you get is worthwhile. So now, remember, as always, we've got to try and understand what's going on here. So the good things to do is to do your summary statistics and your data visualization. And we do data exploration. So explore your data a little bit. And we see there, of the 137,680 diameters we have, the mean was 5.48 kilometers. We see the median was 3.59. And immediately that should ring a little bit of alarm bell, because there's quite a bit of difference between the median and the mean. So we're not going to have nice bell-shaped curve here. And we might run into, this is not a normal distribution. So already when we start thinking about what kind of models we'll have to employ here to be good predictive models, we have to think of the problems that might run into. And I see here when I designed the thing, I was exploring, and there was another one of these variables that was giving me a little bit of a problem, and that was the data arc one. And so we just dropped some there as well. 137,540 is where we ended up. So this process gets repeated. And as I said, you'll have to decide on all of these over and over again. So let's just look at this conditions_code variable. And once again, that was a number, a value, and it was encoded as, or not all of them were encoded correctly. So I used the numeric function and the _numeric function on them as well. So that sort of brought me into a space where most of the problems were fixed. And because we're going to use a regression problem, we would really like all our data to be encoded as numbers and not as text. So if we looked at the neo variable there in that column, df.neo, and we do a value counts, we see that there were two sample space elements. It's a nominal categorical variable, no and yes. So I wanted to change those into numbers, which is a fair thing to do if it's only no, if it's only dichotomous or binary, just to change them into 0 and 1. We don't have to really change that into a one hot encoded vector, because just replacing no with 0 and yes with 1, and that might have meaning. You might have to switch those around. So just for ease of this explanation, I went with the replace function. So I'm overwriting that column. And what I'm doing is using the replace method. And I'm using a Python dictionary there. And I'm saying, if you find n, please replace that with 0. And if you find yes, replace that with 1. So certainly this is the sort of the poor person's way to go about this. You can certainly do your one hot encoding, which is probably better. The same thing with the variable there, and I just used the same replacement, and then called info again, because there was still one little problem. So I have all my predictor variables there. There seems to be no no missing values, and if we look at the D type, there's no more objects there, so I'm pretty sure everything is now a number. And there's only one more problem for me to deal with, and that these are all 64-bit floating numbers. So you see float 64. So the bit size of a floating point value or integer is a computer representation of what the maximum and minimum value is and how many decimal places it can hold. So 64-bit representation of a floating point, a decimal, can hold many more decimal places. But a lot of these architectures, a lot of these algorithms are only written for 32-bit floating point values. So that's kind of the highest bit value or representation that they can handle. So I just have to change all those 64-bit floating point values into 32-bit floating point values. So I wrote a little for loop there. So I said for column in df.columns, remember df.columns, that attribute is just going to return for me all the columns. So I say if df column, so the first one that it's going to find is this first one up here, the A one, and then E, and then I. If if that D type is a float, so I'm not worried about the 64-bit integers, I'm just worried about the floats, then I'm going to recast that type to a 32-bit float. So I'm saying df column equals df column dot as type, and then as a string float 32. So that is just going to turn all of those 64-bit floats into 32-bit floats. And after all of that, and much, kind of heavy-handedness, but that's what it takes. And to say this was heavy-handed, so there's a lot more work that can be done. But this is the kind of work that you have to go through before your data set is in the kind of state that you can use it inside of a machine learning to pass it or to use it in a machine learning model. So now the summary data and visualization. So now we see again how many we have, and we see the summary statistics, and we can also create a histogram of this diameter. I'm curious to see, what this looks like, and of course we have a bit of a problem here with this histogram because the majority of them are small in diameter, and then there's some of the larger ones, some of the named larger asteroids on the side. And so, for one of the reasons to use Plotly, of course, I can just zoom in on this little bit here, and I can zoom in even more. So it's just a question of clicking and dragging and zooming in. So I get this representation of this, obviously massive skewness in our data. It's very right-tailed, positive skewness here. But I get some idea of the problem that I'm dealing with. And what you will have to do really is you have to go through all your feature variables as well and look at them. One easy thing to do in the beginning, remember, is just to do a correlation plot. So let's use Seaborn's heat map function. And there's my correlation plot. And I see if we look at diameter here, diameter is here, some of our variables that are correlated to it seems to be what we have there, Q, what we have is data arc there, number of observations used. And so we can see which of these variables are sort of correlated with. And if you want to do some form of easy linear method, which we'll do right at the end, you can get an idea of which of your variables are correlated with your target variable. So now, a difference between traditional just creating linear models. I mentioned it before, we put all our data into the linear model, and then we would extract an R-squared value or other metrics. Look at your mean squared error or mean absolute error, look at your R-squared value. If you're using inferential statistics, express a probability of your finding, etc. But you use all of your data. If any of you are familiar with logistic regression, of course, we're interested in the odds ratios there. What is the odds of the outcome variable? The outcome variable now being categorical in nature, usually a dichotomous or binary categorical variable. And so we just want to know the probability of one of the classes in that, and the odds at least of one of that outcome, and then between 0 and 1. But you put all the data into that model, and that's not what we do in machine learning. And so even if you use logistic regression or linear regression in machine learning, the idea is to split your data up. So we're going to take some of our data and we're going to remove it. Just at random, we're going to remove a certain subset of our data, and we're going to keep it separate from the model. So we're going to train a model not on all of our data. We're only going to train it on a subset of our data. And how do you decide what percentage of your data should you train on? That depends, of course, on the problem or how many observations you really have. If you have a large number of observations, you can extract, say, for instance, what we're going to do, I think I extracted 20%. So 20% of those asteroid diameters, I just at random take them out, and they sit separately, because what we're going to do after we've built our model, we're going to pass this data that the model has never seen, this machine learning model has not learned from that data. We pass that data to the machine learning model. We know what the answer should look like because we know what the real diameters are, and we can measure what our model predicts versus what the actual values were. And that's one of the key ideas in machine learning and supervised learning, is that we can take some of the values out, keep them separate, because why do we build these models? These are predictive models. That's what machine learning is, or supervised machine learning is all about, generating these predictive models, because we want to deploy them in the real world. So if someone brings us new data, we pass it to this model, and the model makes a prediction, and we want that prediction to be as accurate and as good as possible, usable, such that, that it can be used. So we wanted to generalize well to unseen data. And one way to do it is just to take some of this data that we have here and just take it out. First of all, though, we've got to tell the machine learning algorithm which are our predictor variables, our feature variables, or our independent variables, and which one is our target or our outcome or our dependent variable. And that's what I do here. And I just use two computer variable names, features and target. It's just what I use. And what I'm doing is I'm saying drop the diameter from the columns. We've seen that before, so it's going to do it temporarily because I haven't put in place is true. So in features, I'm going to have all my columns except the diameter. And for my target, it's just the diameter. So I've got these two split up. They are separate now. And now comes the scikit-learn train test split function. So what we pass there is very separately our set of feature variables, our target variable, the test size. There are other arguments, but these would be the important ones to set. The test size, I'm setting that to 20% or the fraction 0.2. So what this train test split function is going to do, it's going to take 20% of my data at random and take it out so that I do not do the machine learning, the learning part of the machine learning on that data. It's completely separate. And I'm setting a random state. So if I run this again, we're all going to get the same result. The train test split function, it exports or returns 4 objects. So I've got to give each of them a name. And that's why I have 4 names here. It takes that 80% of the data and I'm putting that into X-train. So that's 80% of my feature variables, my independent variables goes into X-train. The 20% of the feature variables goes into X-test. And then for the target variable, the 80% I put in Y-train, and the 20% that gets left behind that was taken out, I put in Y-test. So it's always the 2 feature variables and then the two target variables. So you've got to, it returns all 4 and you've got to give a name to all 4 of them. So now I've got my data completely split. I've got my feature variables separate from my target variable, and I've got my training set split from my test set. Very important. So in the last lecture in the series, I used a random forest regressor, and this is exactly what we're going to use here from one of the many machine learning algorithms in scikit-learn. We're going to use this regressor. And if you haven't watched those videos, I'm going to show you here just how easy that is. First of all, we're going to what we call instantiate this class. So this random forest regressor that we imported right at the beginning of the notebook, that's a class, and we have to instantiate it, meaning we create one instance of it. And that instance, we're going to call it forest. And then there's a host of variables that we can set. So I'm just going to show you here, just using the question mark to get into the help section. And if you watch that video or read the notebook or the PDF, you know this is built on decision trees, and you would have a good idea of how these decision trees work, and then how an ensemble technique such as the random forest just generates a bunch of these trees, and it usually uses averaging to decide, and a regression model averages over them to make the best sort of possible calculation or prediction for us for our categorical variable. And these things are the things that we have to decide on. All these arguments in machine learning, we call them hyperparameters. So the parameters are the things that the machine learning model learns from the data. And the hyperparameters are the things that we set as the designers of this model. And so all these arguments pertain to hyperparameters, or almost all of them refer to hyperparameters that we've set. So what I've created here is a very sort of puny small little random forest model. My max depth is only going to be 32. I have, so much data, and I have many variables, of course, but I'm only setting the max depth to 32, and my number of estimators only to 50. So that's very conservative. This is a very small random forest that I'm creating, because in a moment I'm going to run this model, and then we're all going to sit and twiddle our thumbs, because it takes a while, even because we've got so much data. And this is not the most powerful machine that Kaggle gives us behind the scenes. But certainly, so I've made a model that you would not put out in production or expect any miracles from. And if you get into machine learning and into, say, using random forests or support vector machines, etc., you've got to learn about all these, and it becomes sort of an art depending on the data that you're dealing with and how you've got to design these machine learning models by these hyperparameters that you've set. So we've set quite an easy one, but you can read through there. It tells you what all these hyperparameters are then. I just wanted to, I just sort of wanted to show you that X-train, remember, that's still a data frame, but it's separate now. It stands on its own, and this is what we're going to put in as our feature variable. And scikit-learn takes, you don't have to express it as a NumPy matrix. You can just pass a data frame. Last little sanity check here. I just want to make sure that, there was no zeros. I think by this time I was rather paranoid because I think I had run into another mistake, and then I went back up and finished it so that you could see this finished project, this finished product. And now that I have my forest, all I have to do is to use forest.fit. I've instantiated that regressor now. I use the fit method, so forest.fit, and all I have to pass is X-train and Y-train. So my feature variables and my target variable as far as the training set is concerned. The only unfortunate bit of the train test split, it gives back my target vector in the wrong dimensions. And you just have to fix that dimension. And I show you two ways to use it. One is just this travel function, numpy.travel Y-train, and then just puts it in the right dimension for scikit-learn. It's one of those things that you just always do and get used to. And as I said, now the model is going to run. If you understand how decision trees works, you understand what an enormous task I've just given this computer. And of course, with this free setup with Kaggle, you're not going to get the most powerful system. In actual fact, here you'll see the CPU here on the right-hand side. That's been maxed out at the moment. Up here, it's a red up here. So we've got to twiddle our thumbs a little bit. So while this runs, it's going to take a couple of seconds. I'll show you a little bit about scikit-learn. I've decided pre-processing your data is one of the things we've mentioned. And when we've done with this, I'm just going to also run a linear model just so you can see how those two contrast with each other. And there we're going to do a bit of scaling of our data. So you can imagine if you know the process of gradient descent, how we get to minimize, say, a cost function. Certain of your variables are going to be in different units. We saw that we had an expression of kilometers there. Those would be big values. And you can think of your own field. Some units are enormous, and you're going to have values down that column in the thousands, and then a column right next to it, you have decimal values, 0.47. And in many model systems, those two have to compete with each other. And when you do deep neural networks, for instance, that becomes very important because these big values in the thousands, if you have a column with those kind of values, is going to overwhelm columns that are fractions, 0.004, 0.003. So what we want to do is we want to transform or pre-process that data so that they are all sort of fall in the same way. And scikit-learn is particularly powerful in this sense that it has a bunch of these pre-processing classes. For instance, here we see the standard scalar, and I think we've spoken about that before. That's just going to subtract from every value the mean for that variable and divide by its standard deviation. But there's a lot of these other scalars as well, and you really want to scale your data before you do that. And I'm going to show you something very specific about the scaling technique when we get to the linear model. And what I've done is, of course, I have not employed it with the random forest because we can debate that point, I suppose. Is it always needed with a random forest to do that? Then scikit-learn also has this great section on imputing of missing values, and that is well worth a read. And it has these imputers, a simple imputer, an iterative imputer, and I think in the notes I do have some of that. So let's go back to our asteroid model, see if it's finished. Has it finished? Fit? It seems to have so. So now we have our data fitted. We have our model, our machine learning model has now learned from our data, and it thinks it knows, it understands what's going on. And of course, as I said, in this form of artificial intelligence, there's no real intelligence here. There's an algorithm that runs very strictly behind the scenes. So we're not anywhere near artificial general intelligence here. So now that I have my trained forest, I can use the predict method on it. So forest.predict. And now I'm passing that 20% of data that it's never seen to it. and it's now going to make predictions for me. And I'm going to save that as the computer variable y_pred, just because it's sort of descriptive of what is happening. Because now I've got this 20% of data, I know what the real diameters are, and I know now what it's done with this unseen data, what its predictions are. So for that 20% of data, I have now a set of the actual values and predicted values. So now we can use one of the metrics. And of course, in the notes, I do classification problems as well, so where we go through the confusion matrix and the metrics that we have there, all sorts of metrics that we have there for expressing how well our model did. In regression, we can use R². So I'm just passing y_test, the actual values, and y_pred, the predicted values from this 20% of data that it's never seen. And with a very simple little model, I get an R² value here of 0.8. So excellent for a very small, very simplistic random forest model. And what I've done for us here is just to plot out the actual values against the predicted values. So there we see really not too bad. So on our x-axis, the actual diameters, and on our y-axis, the predicted diameters. So that is really it. There is a lot to think about in machine learning. And if we, I suppose, go back to Google here and we search for online books, Python, and we change that to machine learning, you are also going to find many books and many resources for machine learning. And there is really, it's a very exciting world, but I suppose it's a bit of a steep learning curve, at least initially. And what I wanted to bring home for you here is really the fundamentals, those things that you always have to stick through every project. Of course, we can use much more advanced techniques, and then other things become available. The idea that I wanted to leave you with here is you've got to work at your data. You've got to get it into the right order. There's a lot of hard work that goes into that. Number two is you have to have this concept of train test split. In other words, we do split off some of our data. And if we use, for instance, a neural network, we'll do a second split into what we call it from the training set called a validation split, because the neural network can use the validation split and give us an idea of how it's performing as the network learns. So there's some added complexity there, but the basics are as I've shown you now. So let's just move on to linear models. I'm just going to show you scikit-learn can do a linear model as well. And this is another little thing that I mentioned that I'm going to talk about scaling. So we've imported the standard scaler, which is going to do the scaling as I've explained. I'm instantiating it. I'm not passing any arguments to it. I'm just using the bog standard setting, default settings there. So I've instantiated it. I now have an instance of this standard scalar class, and I've called it scalar. And now I'm going to do two things. I'm going to, remember, I have separately my test data and my training data. Now I'm going to transform every variable in my training data by this idea of subtracting the mean and divided by the standard deviation of each of them. And there are three functions there: the fit function, the method, I should say, the fit method, the transform method, and then the two combined, the fit transform method. So fitting means it calculates the means and standard deviations, and transform means it changes the actual values for every column. And you can do both of them in one. So fit the data and transform it using the fit_transform. It just saves you that extra step. So I'm transforming all my values in xtrain. But now I do something different from xtest. So just think about this for a little bit. I have a mean and a standard deviation for each column in my training set or in my data set. So a specific mean and a specific standard deviation. That will be different in the test set, because that test set is separately. If I go down each column now in the test set, there'll be a slightly different mean and a slightly different standard deviation. You cannot scale according to the test set. You cannot scale its values by that mean and that standard deviation. You have to use this mean and the standard deviation of the training set. So this time around, we only use the transform function, not the fit or the fit transform. We don't want to know what the mean and standard deviation is. We're using the mean and standard deviation of our training set here in our test set. That means if we export this model into production, and someone gives us new data, you've written an app and someone imports that data into that app, it's got to be transformed with the mean and standard deviation of the training set that was originally used to do that. So that's what I do here with the scaling. So it's just these extra things that you have to always think about. And then in scikit-learn, it's very easy. I'm just going to create an instance of my linear regression class there, and I'm calling it LR. So let's do that. And a very easy LR.fit. I'm now fitting the train norm. So by the way, yeah, I called that X train underscore norm, and Y train, I fit that. And it's a linear model, so it's very quick to do that calculation. This fitted model also has a predict method, and I'm passing X test norm to it, to the prediction. And we can express an R squared, and I'm going to warn you it's going to look terrible. So I've got an R squared of only 0.46. And we kind of see, what the problem is. And we knew that our data was heavily skewed. So if we look at the actual versus predicted value, you can see the nonlinearity in the problem that we have to deal there. So of course, there are a lot of advanced things that we can do in using generalized linear models or linear models. And certainly we can fix this problem. But I sort of just wanted to show you here that there's a lot of these modeling types in scikit-learn, and you can absolutely have absolute fun with all of them. And that's it. A nice early Friday, early afternoon Friday ending.
Thank you, Jan. That was interesting. I learned a lot there myself. Does anyone have any last few questions? And if you do, can you put in the Q&A?
See that how do we then prevent our new data set to take old mean and standard deviations? I'm not quite sure what you mean by that. So it's very clear that the data that goes into the training, you fit transform that. So, and remember, standard scaling is just one. You get other scaling techniques as well. You don't only have to go with standard scaling. For instance, if we pass image data. So if you think about the JPEG image, it has a certain number of rows and columns of pixels, and that is represented in an 8-bit image with values from 0 to 255. That's the intensity of each of the pixels. And all we do is we divide every value by the maximum. So that ends up being every value gets transformed into this interval between 0 and 1, because there'll be a fraction of the maximum intensity of every pixel. So there's other ways to transform data as well, but the transformation is on the training set, and you use the parameters in this instance with this regression problem is that mean and standard deviation only of the training set. So when you look at the test set, what that scalar function will do now is it'll subtract the mean of the training set from each value and use the training set standard deviation in the denominator of that calculation. And let's see what the next one is. I would like to apply what I learned to my research. Would I be able to ask for advice still after this? And yes, yes, we've already received a couple of emails. I've received a couple of emails for direct help. Please understand that I can't get involved in everyone's work and everyone's dissertation. That might be difficult for me to do. But you can clearly see, I think if there's one thing you can take away from this week is that I'm very enthusiastic about this. I'm very passionate about this work, and I really always try and help as many people as I want. So without extending an open invitation, reach out to me, and if at all possible, with within the limitations that I have, I'd really like to keep this community going, because this has been a very nice experience for me. And say a big thank you to Konshu, for setting this up. And I really want to get this community going. But please also get involved with the larger community of data scientists. And depending where you are in the world or where you are here in South Africa, there's great local communities as well. Excuse me. One place you can go to is Meetup. Meetup is a Meetup, yeah. So you can sign up for, just Google Meetup, and there's it's a website all over the world. And then things get organized in your local city. There's Cape Town, Joburg, everywhere, but it's everywhere in the world. And join these little local meetups. That usually happens after hours, and it used to be face-to-face, but now it's obviously all online. and join these local communities. So Meetup is an excellent place, and find like-minded people, because there's nothing as good in life as if you go to work with like-minded people and you're all interested in the same thing and enthusiastic about the same thing. Most of us will know how it feels like to go to work and you don't see eye to eye with your colleagues. That's a horrible sort of situation. So go and find like-minded people, but certainly, reach out to me, and I'll really try and help as much as limitations allow. So Stephen asked there, the R-squared value is not a good one. Are you referring to the linear one, or even the 80 of the random forest? As I said there, there's many hyperparameters to set. And in the end, it really becomes almost a bit of an art form. Of course, there's a lot of research to understand, better understand these models and turn it more into a science than an art, especially when you get to neural networks, to understand the black box that a deep neural network, can seem to be. But there's certainly lots of these parameters, hyperparameters that you have to set. And the one that I used here, as I mentioned, I created a tiny little random forest. So download Anaconda or Miniconda, install it on your local system. I bet you, irrespective of the hardware you have, it's going to run faster than we've seen here. And you can build, you can build better models. If there's one upgrade, if your computer allows you to do an upgrade, if there's one upgrade you can make, usually in laptops, you can't add a graphics processing unit, but you can add more RAM. If you add more RAM, this 8 gig or 16 gig or 32 gig, if you can get up to 32 gig, your machine will be very happy when you throw these models at it.
Great. Shall we call it an early afternoon, Jan?
Absolutely. I want everyone to have a lovely weekend.
Thank you, everyone. Thanks, Jan, for presenting an amazing course. I learned a lot. It looks like a lot of people had learned a lot as well. I will send out details about the questionnaire sometime today or tomorrow. Give me some time too, because I've got to finish other work. Thanks, Emil, for being here and answering questions throughout the week. That's been really useful. Thanks to you too, Bruce. You were answering some questions earlier as well. Okay, so I'm going to close it off. Thanks, everyone. I will send you the recording. Remember that website. I will also send you the links to that website where you will find all the resources that we've used in this class, as well as links to videos which I had uploaded onto YouTube. Have a good weekend, everyone.
Great stuff. Just the last thing,
when you get the email.
Sorry, I see there people just asking. The best way to reach out to me is to follow me on Twitter and send me a DM. For those who want to connect with me, that is really the place. I suppose I'll answer you as soon as possible. Thank you to everyone. Thank you, Kanchi. Thank you very much.
Cool. Remember, so sorry, Emil, you were going to say something?
No, just thank you. And the week was beautiful and a great introduction to data science and Python.
Thank you very much, Emil. Great stuff. Thank you for being here. I really appreciate it.
And I must say, I've looked at many courses in data science and, and computational thinking, a similar kind of courses, and nothing has gone as deep and explained as well as this one. So well done, Jan. Thank you all. Thanks to all the students for being here. Have a great weekend and keep doing data science. Bye-bye.
Bye-bye.
Yeah.